So, as I mentioned, it's pretty early. So if I seem drowsy, that's my built-in excuse here. But good to meet you all. My name's Tim Hanewich, and I work at Microsoft by day on low-code technologies, and by night, I'm much like you all. I'm a tinkerer. I like to build things with Python, MicroPython, and so forth. And today I wanted to show you and talk to you a little bit about how I built my very first quadcopter flight controller called Scout. It was a very long process, but a fun one. And I hope, all of my efforts and my literal, sweat, blood, not many tears, but plenty of sweat and blood that I put into it can be valued by you all. So thank you for the time today again. So before I start, I wanted to show you a funny little video. I'm not sure if the sound will work here. I'm not sure if the frame rate will be very good, but regardless, I have it on YouTube. I'll make sure Matt sends it out afterwards. But it's a funny video. It kind of just shows, it's a 1 or 2 minute video. It shows the very intensive process to get where I got, where it's finished now last summer. It's a lovely summer for me. So let me go ahead and play it right now for you all.
The video is coming through well, but I haven't got sound, Tim.
Okay. Let me I use Teams at Microsoft by day, so I can't quite figure that one out. But I think that's probably fine, man. Let me just hit play. Don't worry about it.
I think it's fine. Yeah.
It's just the music from Larry David's Curb Your Enthusiasm, if you all know that.
You weren't kidding about the blood, huh?
What was that, Matt?
You weren't kidding about the blood.
No. I literally have a few, if you can see it on camera, a few scars on my hands from this thing too. No, this thing's done some damage. It's permanent for sure. So 70 days, tons of code updates, tons of commits in Git, a few fires and plenty of injuries later, and actually a few blood-stained carpets. And I finally got my quadcopter to fly. And I'll tell you, in that 70-day period, numerous times I thought, I have to quit. I can't continue. It's too difficult. But I persevered. I go to the gym. I go out shopping, and I think, you know what? I haven't tried this idea. So I go home, put it into motion. It would usually not work, but I'd still get frustrated, try it again. And so eventually got it to work. But anyway, it's a really cool project. And what I'll share today is sort of how I built it and why I built it. But please don't think that it was easy. Like if some of you here have tried yourself, you probably know. And if you do try, I'd encourage you to be patient with yourself. It's a hard process. So what I share today is what I learned after a long period of time trying to do this myself, both this year and a couple years ago. So first of all, why did I do this? My background again is in software, and now at Microsoft full time, and before in college, all that I did was software. Everything from my work in making little apps to help me drive better in my racing games on Xbox to financial APIs. Everything I've done was mostly in C#, backend APIs and whatnot. And I've done the absolute basics, like I can make an LED blink on my Raspberry Pi PiCoW, but I really never ventured much into hardware. And I thought this project would be a fun thing to do. For a long time, I've loved quadcopters, and I've been fascinated by how they fly. So I thought applying my software engineering brain to a hardware problem like this would be fun. And it was fun, but also very challenging. So that's why I started it. And that's why I did it. And I thought what would be cool today would be to first explain how quadcopters fly, because I feel like I'd sort of got a PhD in this process. So first of all, airplanes fly pretty intuitively, right? They use active aerodynamic elements like ailerons, spoilers, flaps, rudders to configure their angle of attack over air and to generate lift in any direction. And they use that to both passively fly to stay afloat and to maneuver. The thing is, quadcopters, as you can visually see, have none of those. They have no active, passive aerodynamic elements. In fact, they only have 4 motors which spin propellers. And so the trick here is quadcopters have to stay afloat, and they have to maneuver by strictly varying thrust to those motors. And if at any point one motor is not doing something that it should be doing, the quadcopter will not remain in the air. It's a very challenging thing to do. So some people here might know, but some might not. But what is the role of a quadcopter flight controller? Again, the number one role, it's an onboard chip. Its job is to vary the thrust of each motor independently to maneuver the vehicle, whether it's to bank to the right, to the left, pitch forward, or yaw, whatever it might be. It's to do that. And number two, it's also just simply to maintain stable flight and to find the exact mixture of thrust across all the 4 motors to maintain stable flight, to maintain orientation, and to not abruptly fall out of the sky, which is actually easy to do if you're a quadcopter. So the way they fly is actually fairly intuitive. Again, quadcopter, quad is for 4 motors, and it's not hard to understand how they can maneuver. If you wanted to, for example, move the quadcopter forward, right, pitch forward, intuitively you would apply more thrust to the rear 2 motors and less to the front 2, which would intuitively, pitch the quadcopter forward. If you wanted to move backwards, do the opposite. And to pitch backwards, you would increase thrust to the front 2 and decrease thrust proportionally to the back 2. To pitch, or excuse me, to roll to the right, again, increase thrust to the left, decrease to the right, vice versa for rolling left. And then for yaw, you'll see that the propellers will rotate in different directions on diagonal axes. So the front right and the rear left will rotate anti-clockwise, and the front left and the rear right will rotate clockwise. So by applying more thrust to one diagonal as opposed to the other, you can manage to yaw it either to the right or to the left. So this would be to the right, and the left would be applying more thrust to the clockwise motors. So those are the basic foundations of how the quadcopter moves, and it's up to the flight controller to determine how to apply thrust across those options you saw previously to, again, maneuver and stay afloat. And I thought, I'm in software, it's not hard to figure out maybe some algorithm that can mix together a series of inputs from a pilot and determine the precise level of thrust to apply to each motor. So I did that, and I made my own, MicroPython, my own Python class that did this. And I said, hey, if the pilot inputs, half throttle, 50% throttle, obviously the mean thrust applied across all 4 motors should be 50%. And I think that should probably maintain altitude. It should maintain a steady orientation. And my quadcopter, all 4 of my motors are the same. They should output the same amount of thrust, so it should be a steady, even flight. And I said, if the pilot wanted to turn to the right or wanted to bank to the right by 50%, then I would, again, increase my left motors proportionally and then decrease my right motors proportionally as well to accommodate that left-hand banking. If they then said I want to move forward, it would again do the same. It would mix all together, and it would, ultimately, it would achieve a vector of thrust that would allow me to both bank to the right and pitch forward. And then again, as I would decrease my throttle or increase it, it would simply as well drop down, or it would adjust the mean thrust to accommodate that. And I thought That's all there is to it. As a pilot, I should be good enough to very rapidly make adjustments as needed. But for the most part, this should be how it works. Turns out I was totally wrong, and all of my effort doing that was in vain. This is not the way to make a quadcopter flight controller. Due to numerous reasons, from wind influence to weight distribution, the motors, they're the same, but they're different in how they apply thrust. One might be more powerful while one might be 5% less powerful. They might be mounted, very, very slightly differently on the frame itself. This would not work. And in theory, it might work, but the pilot would never, ever be able to have enough time themselves to rapidly make adjustments on the controls just to keep it afloat. So I did more research, and it turns out that even keeping totally stable, a quadcopter's 4-motor thrust output should look a lot more like this. And I'm not sure if it's coming through for you, but what I have here is a graphic showing you that each of the 4 motors is rapidly changing thrust as we speak. So even from the pilot's perspective, maintaining the same control input, trying to maintain orientation, the actual flight controller itself should be rapidly updating each motor thrust to accommodate and maintain a certain orientation or orientation angle. So that's how they should perform. So really what happens here is the onboard flight controller does a few things. What it does is it constantly, and I mean repeatedly over and over, many times per second, it constantly says, how is my orientation changing, right? How is my actual body changing? And then it says, how does the pilot want my orientation to be changing? So it finds the error, it finds a difference, and it adjusts thrust accordingly. And it's up to the flight controller to determine, through a way I'll show you here in just a moment, to determine exactly how it should apply thrust uniquely across each of the 4 motors to accommodate and accomplish the desired input and fits an error that may have arisen from wind, for example, or weight distribution. And this loop you see here, again, runs at many times per second. So you'll see in commercial instances with DJI, for example, or Betaflight, maybe some of you've heard of that before, sometimes they run literally several thousand times per second, but mine's running at 250 hertz. So my flight controller makes that adjustment 250 times per second. So in the equation, again, it has to know how it's currently, how its orientation is currently changing, and it has to know how the pilot wants it to be changing. So 2 pieces there. The first piece on how it's actually changing, it has to have an onboard IMU. It has to have an onboard gyroscope. So I'm using very common, very inexpensive, easy to use IMU, the MPU 6050. I'm using I2C here in MicroPython to collect data and do so at a very fast rate. And to understand my rated orientation change across the X, Y, and Z axis. So now I know how I'm changing as the flight controller. And then to collect pilot input to understand from the pilot sort of what they want to do, I'm using a FlySky FXIA6B receiver, or I should say, no, sorry, FXIA6B transponder and an FXIA6B receiver on board to collect through RC, radio comms, the pilot input. So now I have both pieces. I know how I'm changing my orientation currently, and I know how the pilot wants me to change. So let's say, for example, at a given moment, this is the situation. Across my pitch and yaw, my pilot wants me to maintain orientation. Do not roll to the right, don't roll to the left, don't pitch, don't yaw, but there's an error, and that error is my quadcopter is actually banking to the left ever so slightly with a minus 25 degrees percent inclination, and the pilot wants me as the quadcopter wants me to maintain orientation. So intuitively and naturally, I think we'd understand that if the quadcopter is banking to the left, it's banking to the left, what that means, and we don't want it to, what that means is we should apply more thrust to the left-hand side and less to the right-hand side. But again, hard coding that algorithm is probably not appropriate. Instead, we should equip our quadcopter with a mathematical model which allows it to more dynamically determine level thrust to apply to each side. And so the question is, again, how should it apply thrust to each of the four motors to get from that minus 25 degree per second roll to 0? And the answer is through a PID controller. It's PID controller, which is, PIDs are commonly used across numerous industries and instances and applications. But a PID controller, for those here that might be new to it, is actually, it sounds intimidating, but it's actually not really hard at all to understand. It's a mathematical model which integrates 3 different components to determine how it should, again, apply power or thrust to get from a current state to a goal state. And PID stands for 3 things. The first term there is proportional, where that component says the thrust that you should apply to each motor should be proportional to the error. So, if the error is 10, for example, it should be proportional to that. So if it's 10, apply a thrust maybe of 5 or half, 5%, for example. If the error is 20, it should be 10. It's proportional to the error directly. I stands for integral, which says that the thrust applied should be proportional to the accumulated error over time. In other words, if there's an error and thus far I can't correct it, I haven't corrected it, as time goes on, as time grows, apply more and more thrust to hopefully overcome that growing error. And then finally, the D term is for derivative. And derivative, it actually does not, it doesn't care about the error overall. It simply cares about the change in error. It cares about the rate of change in the error. So the D term is simply observes, like very twitchy moment of error change instances. It's not caring really about the error over time or entirely. It just wants the orientation to stay the same, really. So this is a PID controller, and what happens is mathematically, of course, in Python here, we have a PID controller class being used, for example, and you would pass into it, again, at any given moment, you'd pass into it the current orientation for all 3 axes and the expected or the goal orientation. And then the output would be, a recommended level of thrust to apply to each side, or each diagonal for that matter, by both the proportional, integral, and derivative terms. So say, for example, in this moment, the P term, proportional, tells me I should increase thrust by 24%. Integral says 8, and derivative says 13. My job as the developer of the quadcopter flight controller has to say, how will I average out these 3 to get to an expected or a final thrust to apply to increase my left-hand motors and decrease my right-hand motors, right? And so that's called PID tuning, which is essentially where you're saying you're applying a weight to each term, and you're saying, based upon what I've seen so far, it's probably better to prioritize the proportional term over the I and D term. So let's just say, for example, I did that and my output was 15. So what I would do here is I would then, actually that's flipped there. It says plus 15 to the right motors, minus 15 to the left. I should have flipped that. But anyway, it's flipped. It's correct here in my diagram. What I should do is I should apply, if my throttle input is 50%, of course, the mean throttle across all 4 should be 50, which it is here, but I should apply that 15% thrust to the left accordingly. And then again, the proportionally same amount, but minus 15% to the right-hand side to accommodate that. So basically, that's how I'm accomplishing this process. That's what I'm accomplishing with a mathematical model, allowing the quadcopter to itself calculate how to apply thrust to each of the four motors across all three axes to hopefully accomplish and achieve the pilot's intended orientation change. So now that we know how much or what percent of thrust to apply to each of the four motors independently, how can we actually get it to do that? I'm sure the team here probably knows a lot about this process, at least more than I do, but I'm using brushless DC motors. These are three-phase power, so it's a series of magnets inside of a turning chamber, if you will, and it's up to me to rapidly change the magnetic power to them to have it rotate, and they have to change at a rapid speed. So I'm using an ESC here between my flight controller, my PiCoW on board, and my motor to achieve that. And I'm using a forest lipo battery and PWM here specifically to actually power my motors. So you see here, I set up each PWM channel, one for each motor. I call it M1, M2, M3, and M4 at 250 Hertz. And the way to power it is actually pretty straightforward. It uses, again, PWM at 250 Hertz. It runs at 4 ms each cycle. And so in my case, for my ESC, this is pretty standard. 0% throttle would be 1 ms duty cycle, and 100% would be 2 ms duty cycle. Of course, with anything in between there being linear between 1 and 2 ms. So I want to talk more about hardware, first of all. My quadcopter uses what's called an F450 frame, a cheap frame off of Amazon. Pretty straightforward, lightweight, simple to use, actually quite large, not really made for performance, but more of just a sturdy thing to use. The cool thing here is that the bottom tray of it actually serves as well as a PDB, a power distribution board. So I'm able to solder my battery to it, and it allows me to very easily distribute power to each of my four motors. My battery, I used a 4S 3300 milliamp hour LiPo battery, which has plenty of power and plenty of flight time, I found. Pretty straightforward there. My motors are 2750 kVs, again, brushless DC motors, which are actually very powerful for this project. These are made for performance quadcopter flying, which mine was never meant to be performance, so I probably could have gotten cheaper ones for that matter. But you live and you learn. And my propellers are 2-vane 8 by 4.5 propellers, which means, of course, there's two vanes here, 8-inch in diameter, so quite large, and a 4.5-inch pitch, which is fairly low, I believe. And then, of course, I have to have between my Raspberry Pi PiCoW and each of my four motors, I have to have an ESC, so I have one per motor between them on each arm. And powering those, or just giving them signal, I have a Raspberry Pi PiCoW, the RP2040, running MicroPython, obviously. Then on board, to collect my current orientation and current telemetry, I have an MPU 6050 IMU, again, cheap, easy to use IMU with I2C. And then again, to collect my the pilot's intended orientation change, I'm using the FlySky FSI-6 and FlySky FSI-6B transponder and receiver. And I won't go deep here into it, but here's my wiring diagram. Not too hard to understand. It's just simply a battery, Raspberry Pi PiCoW, MPU 6050 IMU, and the FlySky receiver with 4 ESCs between the PiCoW and the motor. And by the way, my forest lipo battery is 14.8 volts nominal charge, which is far more than of course than can be taken by the Raspberry Pi PiCoW. So each ESC has a BEC on it, which is a battery eliminator circuit. It allows me to seep from that a 5-volt current to power my PiCoW with, which is pretty neat. So to wrap up here, or towards the end here of my presentation, I want to again point out some simple and a lot of silly challenges I had during this project. So if you do choose to do it yourself, see that wasn't easy for me, and hopefully my challenges and my laborious process here, hopefully you can learn from it and try it yourself. But my first mistake was originally choosing to use UDP as my comm system. So I thought, hey, at first I used a Raspberry Pi PiCoW as internet enabled, and I thought I can simply pair up with my PC here, an Xbox controller over Bluetooth, and send it telemetry or send it input over UDP, maybe once every 0.1 seconds or so. And that would be in my home here, in my living room, how to control my quadcopter. This was an awful idea. So the RP2040, by the way, I think you all know, has 2 cores there. You can have 2 threads going at one time. My first thread would do comms. It would read input over UDP and give it telemetry too. And thread 2 would take the input understood from the first thread and use the PID loop to again do that comparison of current orientation to goal orientation. Turns out this is actually really not good. It's actually as well quite dangerous, because it's not the most stable. And if, for example, something happened where my PiCoW temporarily lost connection to my Wi-Fi router, if the last packet it received was an instruction to go to like 95% throttle, that could be bad, right? It could hit the ceiling, and if I cannot get back on the network again and tell it to calm back down and go to a lower throttle percentage or shut down entirely, it would stay in that state. So this is actually a very dangerous method. Do not do this unless you're confident, and you may be built in also a failsafe that says if you've not received a packet in the last maybe 1 or 2 seconds or so, then just shut down entirely. Number 2 challenge here was the performance from my Pi PiCoW. So again, to accomplish stable flight, this PID loop has to happen rapidly. And my goal here was to hit 250 hertz, 250 times per second. And for a while, I wrote my code, and for a while I was stuck at like 115. I couldn't quite get anywhere close to 250. So I thought, hey, the PiCoW runs at 133 megahertz. Of course, the onboard RP2040 does at least. Why don't I step up to a Raspberry Pi Zero W that has a 1 gigahertz processor on it? So I literally 2 times in this project completely departed from MicroPython, went to Python on a Raspberry Pi Zero W, did my code, ran it. It actually ran slower. It did about 90 to 100 hertz. And I think in hindsight, it's probably obvious, because the Raspberry Pi Zero W has to run an entire OS2. So it's hampered by tons of background processes as well. So that did not work for me at all. So what actually did work for me was, first of all, code optimization, a little bit of it for the most part, but mostly overclocking my RP2040 to 250 megahertz. So pretty straightforward there, which worked for me quite well. And as far as stability goes, it seems just fine. Also, a very frustrating challenge here. I mentioned before that the PID loop has to run at 250 hertz. That's my goal. For a long time, I spent tons of hours getting it there to work, to get to that level with optimization and whatnot. But it never quite worked properly, never quite flew properly, because I realized that I had my PWMs at a frequency of 50. So in fact, what happens here is, while I was updating the PWM, duty cycle, the thrust to each of the 4 motors at 250 times per second, it was not actually being updated on the ESCs to the motors. It was only being updated there at 50 times per second. So there was a massive delay there. It's a silly delay. So I saw that and I said, you know what? I must be an idiot. I updated it. And at 250, it did run properly, fortunately. Also, there's been plenty of bugs in my code, which broke parts of my flight controller and my quadcopter. I've burned through now a few ESCs. I've burned through a few motors too. And I made one mistake where it got locked. I think one or two of them motors got locked into like 100% thrust for a period of time. It completely fried my PDB. So I had to resolder around the frame, just some ugly wires. So it's not the prettiest thing, but it still works. And then as well, my last mistake, again, it seems silly and it's also quite dangerous, but if you do choose to build your own quadcopter, please be sure to apply thrust correctly. You saw my last slide, I did it incorrectly in my graphic there, but for a long time, I had literally been applying thrust incorrectly. So again, if the quadcopter body bends to the left, you should apply thrust to the right-hand side and decrease thrust to the apply thrust to the left-hand side, decrease thrust to the right-hand side. I had it flipped in the software for a long time. So what that did was, as the quadcopter would bank out of control, it would further bank in that direction. So it ended up being some death spiral, which again gave me plenty of injuries and plenty of scars I have now on both hands, which is unfortunate, but it is what it is. I wear it with pride. So real quick, future improvements if I choose to write Scout version 2 in the future, which will be probably in 2024, if anything. I want to have a way to get telemetry from it, first of all. So I want to have a way to get from it like battery voltage, other telemetry from it. So I thought about that. Also in angle mode. So some of you might know, but you know, in quadcopter piloting and flying, there's rate mode and there's angle mode. Rate mode is where the quadcopter only cares about its current rate of change in orientation, but angle mode is where it observes as well the angle to the ground, using, of course, the accelerometer there. So I might want to have in 2 flight modes in the future. Control over Bluetooth possibly, over just simple Bluetooth with the Raspberry Pi PiCoW and MicroPython. Maybe GPS, running lights, and also as well, of course, my code is quite optimized now, but I'm sure it's not the best it could possibly be. So as well for the code optimization, excuse me. So to wrap up here, I want to encourage you all, if you're interested, to try it on your own. And again, it's not an easy process at all. It did take some time. It took some blood and some effort from me, but I think that I hope that you can learn from what I've done, and maybe my efforts and my laborious pain I went through to get this project going. Hopefully that can be used to help you as well in this project. So first of all, rough cost estimate. Not too expensive to actually do this. I bought everything on Amazon myself. By far here, the most expensive pieces of this are the 4 ESCs and the brushless DC motors. I could probably have gotten cheaper ESCs and cheaper motors for that matter. Again, I used like the best performance ones. I didn't know what I needed, but I could probably get that cost down lower as well. But it's not a very expensive project either. I had the cost there in USD and AUD. And all of my code is actually open source. So I have on GitHub here all of my code, the full flight controller code. And on top of that, I released a 12-part series on Medium about how I built the quadcopter, the flight controller, and I delve deeper into each topic from, I2C for the MPU 6050 for telemetry, the Raspberry Pi PiCoW programming, RC receiver receiving data from the pilot and whatnot. And so if you want to, it's all there. It's all written on Medium, publicly available for free. So again, if you have interest, I encourage you to pick it up and try yourself. That being said, thank you. Again, it's fun to do these things, but it's more fun to share it. So I thank you for the time today. With that, I'll open up to Q&A if we have any questions.
Well, first of all, thank you, Tim. That was great. And I mean, one of the things that caught my eye was that 12-part write-up that you gave. It's fantastic reading as well. So yeah, that was good.
Thank you,
I've
Matt.
got a few questions, but does anyone else want to chime in first?
No, you go, Matt.
Sure. So first thing I noticed when you were having your hands getting very close to the propellers, would it make sense to have some sort of propeller guards? Like,
Yes, it would, Matt.
okay.
Thank you. Yeah, it's an awesome idea. Yes. And behind me too, I have a 3D printer. So why I didn't think to do that, I don't know, but it's a really good idea to have one. I think at least at the bottom, but also over the top and the bottom. It would increase weight, but weight actually is not an issue at all. At least for my quadcopter project. In fact, you'll see in my code, I govern the maximum power output, the maximum throttle, to 22% of the overall power.